Hello and welcome back to the lecture on applied econometrics. So we are dealing with a very interesting topic. We are talking about probability distribution, and we have seen Bernoulli trial and Bernoulli distribution and how we can use those concepts for constituting a binomial distribution. Now, when we dealt with binomial distribution, one problem that we faced is that when we have to deal with a large number of trials and we have to get something like we have to sort of get the probability for in each and individual events, it is going to be really difficult task for us to actually calculate that. And we said that there is a possibility, there is a way to actually approximate a binomial distribution to a normal distribution. So now before we actually do that, before we actually get into the theories, let us try to intuitively understand it, let us try to visualize it, how it is happening, and like how we can actually see that in real life. Okay. So I will do that as usual with an example, because that will actually give us a sense of what is happening here. So let us say again, like we take an example, let us say this is a hospital, okay, and hospital has, let us say, 5 doctors. Now it is a time of COVID. So the hospital is really afraid that if the doctors are infected, if all the doctors are infected, or if most of the doctors are infected, how it will run its business or how it will treat people during this tough time. Okay. Now there are 5 doctors, and the probability of getting infected, probability of infection, let us say 20%. So now hospital has, so let us say, called one of you as a statistician to actually help them to actually have a to constitute a probability table of doctors getting infected. So how many doctors will be infected, and what is the probability of each of these individual events. So what do? You basically, let us say we use a simple Excel sheet here, and I have already written it down here. So number of infected and their corresponding probability. So let us say my random variable x, it can be 0, no infection, no doctor infected, x could be 1, x could be equal to 2, x could be equal to 3, x could be equal to 4, or x could be equal to 5. All 5 doctors could be infected. Okay. And you need to, so these are your x's, and you need to create your probability, you need to get your probability. So what do you use? You already have learned binomial distribution, you know how it is to be used, and you use the binomial distribution to sort of write down the probabilities. Now so the first term is the 5, basically there are n is 5 here, x is 0, so 5c0, the first term 5c0 is equal to 1 into your 0 success, or whichever you say. So basically 0.2 power 0, which is equal to 1, and then I have 0.8 power 5. Okay. So 0.8 power 5. So that is the probability of 0% getting infected, so which is 0.32. Now what about 1% getting infected? Probability of 1% getting infected is 5c1, which is 5 into 0.2 is the probability of getting infected, 2 power 1 into 0.8 power 0.8 to the power 4, right, 4. So the 4 persons are not infected and 1 person is infected. So it is this is the value we are going to get. What about 2% getting infected? So now it is 5c2, which is 10 into 0.2 power 2, I have 2% infected, and I have 0.8 to the power 3, because 3 persons are not infected. So the probability is going to be 0.20 something. Okay. Now what about 3% getting infected? So it is going to be 5c3. Okay, 5c3 is again 10. 5c3 into your 0.2 power 3 into 0.8 power 2. So that is going to give you something like a 0.05. What about 4% getting infected? So 5c4 is equal to 5 into into 0.2 power 4 into 0.8 power 1, right, 0.8 power 1. So, that is going to give you a value of 0.006. Now, what about 5%? All 5% getting infected. Okay. So, if all 5% have to be infected, so you have to have 5C5 which is 1 and 0.2 power 5, and the last term is going to be 0.8 power 0 which is 1. So, basically what you will have is 0.2 power 5, okay, and that is going to give you this value. Okay. So, if you add them up, of course, this total will be 1. Now, the reason I actually took the pain of actually deriving each of these probability values is to give you a sense how the distribution looks like. If I really plot it, so it is like somewhat skewed, sort of you can think of a normal distribution somewhat skewed. Now, so this is what we are going to see if I have the these values here. Now, we will do some more intuitive understanding, we will build some more intuitive understanding here. So, one thing we have done is that we have actually got a probability of success is to be 0.2. Now, I want to actually change that, I want to make it let us say 0.5, okay. This is like symmetric, okay. So, success and failure is going to be symmetric. So, here P is equal to 0.2 and I am going to do another probability calculation, probability where P is equal to let us say 0.5, where P is equal to 0.5, okay. And here what I will see is, if I again let us again do the exercise, and there is a reason we want to do the exercise, I will just see that. So, again if x is equal to 0, so we will simply use the formula. So, it is 0.8. So, let me actually copy the whole thing here. So, here I have instead of 0.8, I will simply replace it with 0.5. Okay. So, the success rate is 0.5 instead of 0.8, here it is going to be 0.5 and this is also 0.5. So, I get a value here, I am doing it mechanically. So, 0.5, all I am doing is I am changing the probabilities, the n remains same, 0.5, 0.5, and here again I change to 0.5 and 0.5, and we see this, and here of course I change it to 0.5. So, I see this, okay. Now, why did I do that? Now, let me actually plot it and let us see what we get if we plot it. So, I am going to plot this one, insert, can I not add one? Let me see. Yeah, here I get. So, what is happening here, you see this one is skewed, but this one is more sort of symmetric. This particular when I had probability equal to 0.5, I get a more symmetric distribution vis-a-vis what I got when I got probability p equal to 0.2. So, the point I am trying to make here is that if I have the probability of success and probability of failure almost equal, I am going to get a symmetric distribution. And the second point I am going to make is, which I am not going to show you, is that if I keep on increasing the number of trials, okay, here I have only like 6 trials 0 to 5, but if I keep on increasing the trials, what I am going to see is I will be seeing more sort of this curve to be more coming close and getting dense, and we can see a more sort of symmetric distribution like a bell shaped curve we will see, okay, and that bell shaped curve is nothing but our normal approximation of a binomial trial, right, okay. So, for example, if instead of, and that is really helpful because we cannot really afford to calculate all the probabilities for all the different events. So, for example, if instead of 5 doctors I had 60 doctors, let us say, and out of those 60 doctors I had to calculate that at least 40 doctors will be healthy, they are not infected. So, I have to basically calculate 20 possible events where the doctors could be infected, and I have to subtract that from 1. So, that is really difficult task. But Instead, I can use a normal distribution, and where I have, fortunately for us, all the z, I can convert that into a standard normal distribution. I can get the z values, and we will talk about all these details in the next lecture. So, there we can simply use the z values, and we have already a z table for us, and we can use the z table to actually see the probability corresponding to each of this z value. So, that is where we will see the results are coming similar or same basically for binomial as well as for normal. So, that is the idea of normal approximation of the binomial distribution, and with this we sort of end our discussion on binomial distribution. We will again revisit when we sort of introduce the normal distribution, but before that in the next lecture we are going to talk about some fundamental theorems that are really crucial for building many models that we are going to build going forward, and that is a building block. So, we are going to talk about these theorems in the next lecture. With this, we end our lecture on binomial distribution. Thank you.